Hello, my name is Hallie, and welcome to this exploration of polyvalency and normality. Polyvalency won't apply to every compound that you see on test day, but when it does apply, it gives you a lot of information about the strength of an acid or base in solution, and unfortunately, when test takers forget to take polyvalency into account, it can make it hard for them to predict the correct answer because it does affect the stoichiometry of your equations. However, we will also identify two formulas which will help you to master polyvalency on test day. And by completing this review, you'll be able to look at different species of acids and bases and identify what molar equivalents of the acidic and basic protons will each of those species be able to generate. And you'll also be able to evaluate questions such as the one at the bottom of the screen, which asks you to calculate the normality of a specific ion in a specified volume of solvent. At this point in your MCAT studies, you've probably had multiple opportunities to explore acids and bases, and you know that these molecules are able to release either hydrogen or hydroxide ions. And when 1 mole of either of these ions are produced, we would refer to it as releasing either an acidic or basic equivalent. And get comfortable with the term equivalent because it's going to come up a lot in this review. Let's look at a standard acid like chloric acid. When chloric acid is placed into solution, it will dissociate, releasing 1 mole of hydrogen protons, or 1 acidic equivalent. And for this reason, chloric acid is a monoprotic acid. However, on test day, you may encounter acids or bases that are actually polyprotic, such as sulfuric and phosphoric acid. When sulfuric acid is thrown into solution, it will actually dissociate twice, releasing 2 moles of hydrogen protons, or 2 acidic equivalents. And phosphoric acid has the ability to release 3 acidic equivalents. And for this reason, sulfuric acid is referred to as a diprotic acid, and phosphoric acid is referred to as a triprotic acid. Now, you may already be able to predict how this can cause some problems on test day when you're asked to calculate the pH of a solution or asked how many moles of base are required to neutralize a compound. However, there are 2 formulas that you'll want to remember in order to correct for polyvalency. The first equation that we can use to correct for polyvalency is the normality of a solution. And all we need to know to find the normality is the molarity or concentration of the solution times the number of equivalents that acid or base can release. Let's look at an example, such as the flask at the bottom right-hand corner of the screen, which has 0.1 moles of sulfuric acid in a liter of water. And we've already identified that sulfuric acid can release 2 acidic equivalents. Let's find the normality of this solution. First, we'll just need to find the molarity, which is going to be 0.1 moles of sulfuric acid per liter of water, and we're going to multiply this by the ratio of equivalents that can be released per mole of sulfuric acid, which is going to be 2 hydrogen equivalents per mole of sulfuric acid. The moles of sulfuric acid will cancel out, and we'll be left with 0.2 hydrogen equivalents per liter of water, or a normality of 0.2. Calculating normality becomes very important when doing certain problems, such as neutralization reactions, titrations, or quantitative electrolysis. For example, if we had treated sulfuric acid as if it were a monoprotic acid, we would have assumed that only 0.1 moles of base would be required to fully neutralize our sulfuric acid. Thanks to the normality equation, we can now see that we would actually require 0.2 moles of base to fully neutralize sulfuric acid. So you can see how the normality equation can correct for polyvalency and why this will be an important skill on test day. The second formula to help us take into account all the acidic or basic equivalents in a solution will be the gram equivalent weight. And gram equivalent weight is very similar to normality, but instead of using the molarity of a solution, we're going to use the molecular weight of the polyvalent. So to find the gram equivalent weight, we would take the molecular mass of the polyvalent and multiply it by the ratio of the moles of polyvalent to the number of equivalents that polyvalent will release. Let's find the gram equivalent weight for phosphoric acid. We will start with the molecular weight of phosphoric acid, which is 98 grams per mole, and multiply this by the ratio that for every 1 mole of phosphoric acid, we will release 3 acidic equivalents. The moles of phosphoric acid will cancel out, and we find that the gram equivalent weight of phosphoric acid is 32.7 grams per acidic equivalent. So if we want to add 1 acidic equivalent to a solution, we could simply just place 32.7 grams of phosphoric acid in that solution. Let's try some practice questions, such as this one, which asks us to correctly identify what type of molecule is being described here and what's the best way to neutralize this molecule. And the correct answer is A. We were told that our unknown has a molecular weight of 190 atomic mass units, but its gram equivalent weight was only 95, which is half of the molecular weight. So this must be a diprotic acid. So Roman numeral number 1 is correct. And for that reason, we can eliminate Roman numeral number 2 because 1 mole of a monoprotic base will not be able to fully neutralize our diprotic acid. And Roman numeral number 3 is incorrect because even though it did give us a diprotic acid, it's an acid, so it won't be able to neutralize our unknown acid. We can also attack questions which asks us to calculate the number of grams required to create a 1 normality solution. And the correct answer is B. Potassium carbonate can dissociate into 1 carbonate ion, and this carbonate ion is able to create carbonic acid, which will release 2 basic equivalents. So, potassium carbonate is actually dibasic and has a molecular weight of 138 grams. When we plug this into our normality equation, we find that only 27.6, or rounded up to 28 grams of potassium carbonate is required to create a 1 normality solution in 0.4 liters of water. Let's highlight the key takeaways that we want to remember for test day. Normality and gram equivalent weight will help us to correct for the polyvalent activity of acids and bases. Remember that most polyvalent molecules will either be diprotic or triprotic, such as our dear friend sulfuric acid, and they will release multiple acid or basic equivalents into a solution. Normality will be a higher number than our molarity because it's evaluating how many acid or base equivalents will be released per mole of our acid or base, and gram equivalent weight will be lower because it's calculating the number of grams required to release 1 acid or base equivalent. But remember, not every problem that you run into on test day will require you to take polyvalency into account. But when you do recognize a polyvalent molecule, make sure that you use normality or gram equivalent weight to correct for the amount of acid or base that will be required to neutralize or titrate your polyvalent. Well, congratulations on completing this review. Now that you have a better ability to identify polyvalent molecules, as well as a familiarity with normality and gram equivalent weight equations, you'll have a better ability to attack questions such as titration problems on the general chemistry portion of your exam. Thank you for joining me, and as always, best of luck on your MCAT.